Hello guys, today we'll be going with the 1991 IMO shortlist problem 17. So find all positive integer solutions x, y, z of the equation 3 to the x plus 4 to the y is equal to 5 to the z. Okay, so on first glance we know that the ordered pair 2, 2, 2 works as 3 squared plus 4 squared is equal to 5 squared. But we also need to prove that because there could be other integer solutions that work here. So first let's take mod 3, and taking mod 3 we get that 1 to the y, or just 1, is equal to 5, which is negative 1 to the power of z mod 3. So this tells us that z is even. It tells us that z is even. And so now let's take mod 4. Now we get negative 1 to the x is equal to 1 to the z, which is just 1. Mod 4. So this tells us that z is even and x is even. Let me just rewrite these. Now taking mod 5, we get negative 2 to the x plus negative 1 to the y is equal to 0 mod 5. Zero mod 5. And so basically, if y is odd, then 2 to the x is equal to 1 mod 5. And so this means that x is, well, negative 2 to the x, this means that x is equal to a multiple of 4. This means that x is equal to a multiple of 4. This means that x is equal to a multiple of 4. And so next, if y is even, then this means that negative 2 to the x is equal to 4 mod 5. So this means that x is equal to 0 mod 2. So either way, we know that x is even and z is even. So now, let's move on to the next part of the problem. So now we can set x is equal to 2a and z is equal to 2b. And so from this, we can say that 3 to the 2a plus 4 to the y is equal to 5 to the 2b. And so now let's do difference of squares. So 4y is equal to 5b minus 3a. Or no, let's not do b, let's do c. Because we can just leave b for a y. It just makes more sense. So 5. And now since 4 to the y is a power of 2, we know that both of these have to be power of 2 because powers of 2 multiply to powers of 2. So let's let this be 2 to the m and let's let this be 2 to the n. So now adding these two equations together, we know that 5c is equal to 5 to the c is equal to 2m minus 1 plus 2n minus 1. 5 to the c is always odd, which means that one of these has to equal 1. And so since m is always less than n, because, well, obviously positive minus positive, positive plus positive, m is less than n, which means that m has to equal 1 here. So m is equal to 1, and this is now equal to 2. And now, 5 to the c is equal to 2 to the n minus 1 plus 2. 2 to the n plus 1 minus 1 plus 1. And so, now we also want to find what 3 to the a is. So 3 to the a is equal to, let's subtract these. So 2 to the n minus 1 minus 2. And so doing this, we get 5c plus 3a, 3 to the a minus 5 to the c plus 3 to the a. So this gets us 2 to the n minus 1 minus 1. So now what we can do is, taking mod 3 on this equation, 1 is equal to negative 1. No, sorry, not 1. Taking mod 3 in this equation, we know that 1 is equal to negative 1 to the n minus 1 mod 3, which means that n minus 1 is an even number. So this means that let's let n minus 1 is equal to 2t. So now we know that 3 to the a is equal to 2 to the 2t minus 1. And so now let's add these two equations. So 3 to the a plus 5 to the c is equal to, wait. Okay, so now we have n minus 1 is equal to 2t. And so now doing difference of squares here, we get 3 to the a is equal to 2 to the t minus 1 times 2 to the t plus 1. And so since 3 to the a is always a multiple of 3, well, no. Even on top of that, we know that these two have a gap of 2, and they both have to be powers of 3. So the only powers of 3 that are 2 gap away from each other are 1 and 3. So this means that t is equal to 1. So if t is equal to 1, n minus 1 is equal to 2, or n is equal to 3. And since n is equal to 3, c is equal to 1, and a is equal to 1. And so since c and a are equal to 1, x is equal to 2, and z is equal to 2. And so now plugging it back into this equation right here, 9 plus 4 to the y is equal to 25. So y is also equal to 2. And so in fact, our only solution is 2, 2, 2. And this is proven. Thank you guys for watching.